is a two-way frequency chart, and this is kind of like data that gets collected in the real world. They're collecting data on just a questionnaire. Check male or female, check going to college or not going to college, okay? And what they're really after is trying to, if someone's doing this sort of research and asking these two questions, they're probably trying to figure out if your gender has anything to do with the likelihood of you going to college or not going to college. What do you guys think? Do you think gender, do you think, if we took the statistics for the entire country, do you think you'd find that females or males are more likely to go to college? You think you would? Who do you think would be more likely to go to college? Probably female. What would be your reason? Or military. Could be. There's definitely more males in the military, so that could be a logical reason. And maybe you would find nothing, but maybe that's why people are suspicious. So how would they find out? They would do maybe some sort of questionnaire, and we're going to look at evaluating what does this data then tell you. Okay, so there's 52 people where this is just in one school, so this is 52 seniors. There's your total. Okay, of your 52 seniors, 22 were female and 30 were male, and then of those 52 seniors, 29 said they were going to college, and then 23 said they were not going to college. So, and then obviously there's the breakdown of being specific in between. So, just giving values, and these are all little lowercase n. So, what is the number of males? 30. Number of females? 22. Number of going to college, C stands for college, so number going to college, 29. Number not going to college, 23. Okay, those are pretty straightforward. What is the number of males, people who are males and going to college? So males and going to college would be right there, 16. Number of females and going to college, 13. Number of people who are either female or are going to college. Probably the trickiest one of the bunch. Female or going to college. Think about this on your own. I don't think so. Where are you getting that from? Your female number is 22. But you also have to include all the males who are still going to college, because they would be counted, right? Andrew, what do you think? Where are you getting that from? So 29. Well, this 29 already counts the 13. This 29 going to college means 16 males, 13 females. Lydia, where are you getting that from? So she counted all of her females and all the people going to college, but by doing that, she double counted the females who were going to college. So she then took that off. Yes? That is one way of doing it. So another way, did anyone do it a different way? Another way would be to count all your females, because they apply. And then the only people that you haven't counted are the males who are going to college. Yes? And so then you could take that 22 and add on the 16. Either way, 32, would you say 38? Either way, 38 is the answer. What we have talked about the past couple of days that I'm going to bring up again is OR means what operation? Addition. But you always have to remember to subtract what you counted twice. So that would be your number of females plus your number going to college minus your number that's both, which in symbolic form I'll say female and college. So you add them up separately and subtract what was double counted. Okay? So if we jump to B, what is the probability that a person picked at random would be a female who is also going to college? They didn't have the word also there, but I threw it in there because it helps reinforce what we're getting at. How many, well, obviously it's out of 52. Yes, there's 52 people we're picking from. How many of them are females who are going to college? 13. So there it is, 13 out of 52. Don't worry about that represent part. In C, what is the probability that a person picked at random, so this is out of 52 again, would be a female or someone who is going to college? How many out of the 52 that were surveyed are female or going to college that would say yes to one of those two questions? 38. That's kind of what we did in part 7. 38 out of 52 are either female or going to college, and some are both, but that's okay. We already didn't, we took away the double counting. Okay, D is, we're not going to explain it in words. This is kind of what we're getting at. You can't just add them together because you're double counting. So just write double counting. The real law is the probability of A plus the probability of B minus the probability of both. And honestly, the better symbolic form of both is to minus the probability of A and B. Anybody that fell in both would have been A and B. Okay, so we kind of had been talking about that over the past couple days. But this just reinforces it in its own separate day. Okay, exercise 5, we have a standard 6-sided die. So 1 through 6 can pop up. Find the probability that the number rolled was either an even or a multiple of 3. So probability of even or multiple of 3. I'm just going to write, maybe I'll do M3, multiple of 3, so it doesn't. So what is the probability of being even? 3/6. Plus, what is the probability of rolling a multiple of 3? Connor, how many multiples of 3 are there? 2 out of 6. Very good. Minus, what's both? How many of them are both? How many out of the 6 qualify as being both even and a multiple of 3? Just one of the 6. Which number was that? 6, right? 6 is even and 6 is a multiple of 3. So you have to subtract that 1 out of 6 because you double counted it. So 5/6 minus 1/6 is 4/6, which is 2/3. So you might ask yourself, well, why would I do it this way? Why wouldn't I just list my sample space and say, okay, how many of those are even or a multiple of 3? Well, there are my even ones, and then my multiples of 3 are just this one, and I had already checked this one anyway, so boom, 4 out of 6. Of course, you might, but this is a very small example. If your sample space gets gigantic, you definitely want to use the shortcut in the equation. Maybe you prefer to use that anyway. But also, seeing both ways pan out to be the same answer is just helpful, I think, to make sense of it all. Okie doke. Exercise 6. Insurance companies typically try to sell many different policies to the same customers. At one such company, 56% of all of the customers have car insurance, 48% have home insurance, and 18% have both. What does this scream to you, hopefully? Venn diagram. You've got individual percentages plus a both kind of situation. So let's make a Venn diagram. What should we label each circle? Car, I'll do on the left. Home, I'll do on the right. Very good. So let's go back to the start of these numbers. And this is already, you see what I'm talking about? Like reading once, reading twice, reading 3 times. So you go back to your numbers. 56% of all customers have car insurance. Unfortunately, I can't do anything with that 56 right away because these 2 sections make up the car circle. They need to add up to 56. I don't magically just split it up any way I feel like it. Same thing with the 48 for home. 48, these 2 numbers have to add up to 48. I'm just not sure how they're split until I read this next part. This is going to give me everything. 18% have both. So if you plug in 18% in the middle, now you can go back and look at your car total. Your car total is supposed to be 56, but 18 of those are already accounted for. So what's just the car insurance? 38. So 38% have just car insurance. 18% have car and home. And then if your home circle is supposed to be 48 total, what goes here? 30. So 30% have just homeowners insurance. And then, don't ever forget about this. What percentage have neither? 14, because these add up to 68, 78, 86. 86%, so we're still missing 14% of the people. Maybe they have life insurance. Only life insurance, right? And Venn diagrams, by the way, can have 3 circles. We'll see an example of that over the next couple days. We'll get there. But there's your situation. So now find the probability that she or he has at least one of the policies. So which of these numbers fall in at least one of the policies, Cameron? Do these people have at least one of the policies? Yeah, which one do they have? The car. Do these people have at least one of the policies? So does that qualify as at least one? Yep. Do these people have at least one policy? Do these people? No. So at least one policy are these 3 numbers. So if we add those percentages together, 68, 78, 86% have at least one. Now, probability, 0.86. Probability is technically a number between 0 and 1. We often turn it into a percentage because we think about chance. There's an 86% chance, but technically probability is a number between 0 and 1. And then B, find the probability that she or he has neither. And we already did that, 14%, so 0.14. Okay? Any questions? All right. This is big. Conditional probability has come up a lot on the regions. And actually, let me go back to this original thing because we're going to revisit it. Has anybody made any conclusion as to what this data shows us, or we're just looking at the results of our survey? Does it look like females are any more or less likely to go to college? Certainly, if you look at the number of females who go to college and the number of males who go to college, well, it looks like more males go to college. But what would someone defending that say? Why might the males be higher, Nate? Because there's more of them to begin with. So does that difference make up for the fact that there was a difference in just the sheer number of males and females? And this is what statistical analysis will tell us. And we have to know how to interpret this data. Yep. Yes. One thing you're going to find with stats and probability in all of this is, and hopefully this makes you a little bit more distrusting when you read stuff or you hear things on the news about this percentage of people does this, that. Listen, you can make stats say whatever you want. So if there's someone that wants to claim that males are more likely to go to college, they're just going to show you this number. Sure. They're going to say, we did research and we found that out of our people that we studied, more males went to college than females that went to college. They're not lying, but they're not giving you the whole truth either. The devil's advocate will say, yes, more males went to college of that group, but that's because more males were surveyed, and they'll give you the whole story. So when you hear people throw numbers at you, that sounds really powerful, but if you really ask good questions and you learn to be suspicious in the right ways, like someone wants to tell their claim, they're only going to tell you part of the story. They're going to tell you the numbers that back them up. And you really can make statistics lie. So on the regions, we will tell you, when you see an explain question, do you think such and such? Your answers doesn't really matter. Yes, I think so, or no, I don't think so. It's the explanation that you give that's going to determine whether or not you get that question right. Because you really can argue anything in stats, okay? So this will help us, this conditional probability idea will help us get closer to actually the fact of, is there a significant issue between males versus females and who goes to college and who doesn't. So same chart, same numbers from the front side. It starts small. What is the probability that we pick a female? 22 out of 52? And what is the probability of picking someone that goes to college? 29 out of 52. And here's conditional probability. And there's a new notation. What is the probability of going to college given that we already know you're a female? So as soon as you're given that it has to be a female already, you're just looking at your female column. What is the probability given that you're already a female? So now we're talking about a different total. We're talking about only looking at 22 candidates. Because you have to be already given that you're a female to even be considered here. So out of the 22 females, once we already know you're a female, now what are the chances that you go to college? 13 out of 22? If you already have to be a female, there's a 13 out of 22 chance that you are going to college. Okay? And that is conditional probability. This limits the population that you're looking at. You're no longer looking at the 52. It's just out of the females. So there's things that we'll look at. What was the probability of going to college? (29 out of 52), which is what percentage? 29 out of 52, I'll just do it as a decimal. 50.56, okay? There's a 56% chance that anyone is going to college. This one tells you, okay, well, if you're a female, is your percentage chance of going to college going to go up from 56% or down from 56%? So 13 out of 22 gives us 0.59. So going to college, if you're just anybody, there's a 56% chance. If you're a female, though, has that chance increased or decreased? Increased, not by a ton, but slightly. So does this confirm or at least help Isaiah's hypothesis or no? It does. It does. It says by being a female, you've just increased your chances of going to college. So maybe there is something to that. How significant is this? Is it just coincidence? Could be. And that's all stuff that has to be thought about and weighed, because that's not a huge difference. But if this went from 56% to 95%, would you be more convinced that something weird's going on? Yes. But very subtly, this does show, this particular group of 52 and the results that we got, this does show that being a female increases your chances of going to college. And those are the two things that you compare. You compare your chances of going to college alone, and then you check your chances of going to college given that you're a female and see how that has changed. Does that make sense? So not that this is asking it, but I want to do this as well. Obviously, we know our probability of going to college is 0.56. Let's look at your probability of going to college given that you're a male. What do you think is going to happen? Probably going to go down, right? If being a female helped your chances, then being a male is probably going to hurt your chances. Not a ton, but slightly. So how do we calculate this? Let's review again. This is your probability of going to college given that you're a male. So you're limiting your population to just the males, which is just this out of 30 category. So you just limit yourself to the male column. So given that you're a male, out of those 30 people, how many of them went to college? 16. And 16 out of 30 is 0.53. So being a female made it go up by 3%, and so to balance that out, being a male made it go down by 3%. Does that make sense? Okay, and now the difference between how many males we surveyed and how many females we surveyed has kind of been nullified. It doesn't really matter anymore. We've leveled the playing field and looked at something that kind of made up for that. But still, you could have your argumentative kind of a liar, but not really, that says, nope, males are more likely to go to college because 16 of them versus 13 females are going to college. And they just choose not to tell you all of the story. Are we good? Okay. So which is more likely? That a person picked at random will be going to college given that they are a male, so this one, or that a person is a male given that they're going to college. Shockingly, these are probably not going to be the same number. Okay? So, let's look at it. First, this one. The probability of going to college given that you're a male. We already did this. So we already limited our population to the males, so that's out of 30, and 16 of them were going to college, and we found that was 0.53. The flip of that says the probability of being a male given that you're going to college. So if you think about that, that says something slightly different. If we already know you're going to college, so we're looking at just the going to college row. So out of those 29 people that are going to college, how many of those are male? 16. So if we know you're going to college, 16 out of 29 is 55% of them are males. Good? So they say something slightly different. Are there any questions? Okay. So we will do more with conditional probability tomorrow because there's the culmination of where you're going to use conditional probability will come tomorrow. For the moment, though, I have